Welcome. In this session, we will be looking at particle swarm optimization. This will be our second meta heuristic that we will be studying. The previous technique that we had studied was teaching learning based optimization. Particle swarm optimization is a swarm intelligence technique. Swarm intelligence is defined as any attempt to design algorithms or distributed problem solving devices that are inspired by the collective behavior of social insect colonies and other animal societies. So, particle swarm optimization gets its inspiration from the flocking of birds or what is called as fish schooling. Some of the examples of swarms are bees swarming around their hive, ant colony with individual agents as ants, flock of birds is a swarm of birds, immune system is a swarm of cells, and a crowd can be considered as a swarm of people. The two important properties of swarm intelligent behavior are self-organization and division of labor. By self-organization, we mean that the interactions are executed on the basis of purely local information without any relation to the global pattern. Self-organization consists of positive feedback, negative feedback, fluctuations and multiple interactions. By division of labor, we mean that the tasks that are to be performed are performed simultaneously by specialized individuals. This is what constitutes as swarm intelligence. Particle swarm optimization was proposed by Kennedy and Eberhardt in 1995. It was presented in the International Conference of Neural Networks in Australia. Ever since it has gained a lot of attention. So, right now if we see, it has more than 20,000 paper citations. Right. So, this shows over the years how people have taken to particle swarm optimization. So, as we can see, it is exponential increase over here in the number of publications that have cited particle swarm optimization. So, again particle swarm optimization, as it is a meta heuristic technique, we have been telling it multiple times that it does not matter which domain we are working in. Meta heuristic techniques can always be used as and when we have a optimization problem, especially when the problems are nonlinear or mixed integer nonlinear programming, or even when our problem is black box optimization problem. So, as we can see, particle swarm optimization has been used in engineering, computer science, decision sciences and also in social sciences. This plot shows the comparison between TLBO and PSO. So, obviously it is unfair to compare given that TLBO has been recently proposed, whereas particle swarm optimization was proposed way back in 95, but still what we can see is that people have started to use TLBO, as can be seen over here. So, particle swarm optimization models the social behavior of bird flocking or fish schooling. So, the inspiration is bird flocking and fish schooling. So, the solution, what we call it as a solution in optimization is known as particle or bird in particle swarm optimization. So, each particle or bird has a position and velocity associated with it. In real life, these particles keep changing their position by adjusting their velocity. So, they primarily do this either to seek food or to avoid predators or to identify optimized environmental parameters. There can be more than one reason for which the particles may be changing their positions. A significant difference between TLBO and PSO is that each particle memorizes the best location identified by it. So, it is more like we keep track of our own best. So, each particle keeps track of its best location identified by it. The particle will have that position in its memory and will still keep exploring the search space, but it nevertheless memorizes its best location. So, particles communicate the information regarding the best location explored by them. So, all the particles communicate their own best location, and from this the best location, the best of the individual particles can be located, that would be the global best. So, velocity of the particles are modified by using flying experience of the particular particle. So, every particle has a velocity associated with it. So, how do we modify this velocity? By using the flying experience of that particular particle as well as the entire group. So, in particle swarm optimization, the first step is to initialize the position and velocity of the particles. So, these are generated randomly within the search space, similar to what we did in teaching learning based optimization. So, this will be our particles, collection of our particles, or more familiarly what we will be calling as population in meta heuristic techniques. So, each particle will be associated with its velocity. So, these are the two equations which will govern the generation of new solution, right. So, here W is known as the inertia of the particles, C1 and C2 are acceleration coefficients, right. So, these 3 parameters have to be provided by the user in addition to the termination criteria or the number of iterations or generations or cycles, whatever we choose to call it, and the population size NP. So, in addition to these 2 parameters, the user is also supposed to give the inertia and the acceleration coefficient. There are 2 acceleration coefficients, right. So, here Vi is the velocity of the particular particle, right. So, this equation gives us a procedure to update the velocity, right. So, the current velocity will be a function of the previous velocity. So, that is why this term velocity appears over here, right. So, this R1 and R2 are random numbers, right, random numbers that belong in the space 0 to 1, right. They will be of 1 cross D. So, it will have 1 row and D columns, where D is the number of decision variables. So, for each decision variable we will require 1 random number for this R1 and 1 random number for this R2, right. So, basically for every decision variable we will require 2 random numbers, 1 over here, 1 over here, right. P best of I corresponds to the best location identified by the particle so far, not its current position, but the best position that it has identified till any given point of time. Xi is its current position. G best is the global best, right. It is the best among all. So, there is no G best for every individual particle, right. G best is for the entire population, whereas P best is for every individual particle member, and Xi is again the position of the particle in the previous iteration, right. So, how do we update? So, we determine this velocity and use this velocity and the current position, right, this newly determined velocity from this equation and the current position to find out the new position. So, here I does not indicate iteration, I indicates the ith particle, right. So, if you want to include iteration over here, so in the t plus 1th iteration, this is what is in the tth iteration, and this is what was determined in the t plus 1th iteration. So, this will be t plus 1 and this will be t, this will be of tth iteration, this will be also what is found in t plus 1th iteration, right, t plus 1th iteration, because it may happen that the 4th solution might have updated the G best. So, whatever is the updated G best, that is what we will be using, right. So, P best obviously will come from the previous iteration, that is how we can include the iteration in these equations, right. To keep it simple, we did not include the iteration over here. So, as we will do one example, you will be able to better understand that. Once the position of a new particle has been identified, we need to evaluate its objective function or the fitness function and update the population. Remember, we need to update the population irrespective of the fitness. There is no greedy search involved over here. The position is definitely going to be updated, right. Whether the solution is good or bad does not matter, it will be included in the population, right. This is unlike TLBO, wherein we employed a greedy selection mechanism. If and only if the new solution was good, it was taken into the population. In PSO, it is not like that. The new position is always going to be taken into the population, right. So, that is one major difference between TLBO and particle swarm optimization. The next step is to update the P best and G best. Given that we have generated a new solution over here, right, this solution may be better than its own best, or it may even be better than the global best. So, we check this condition that the new solution which we have generated, if its fitness function is denoted by f of I, and if it is less than the fitness function of the best position of the ith particle, right. If this condition is satisfied, then we update the P best of the ith solution and Fp best of the ith solution. So, P best stores the values of the decision variable and f of P best stores the value of the fitness function, right. Here it is more like a greedy selection strategy, that once we generate a new solution, if the solution is good or bad, it is definitely going to be included in the population, but the P best and the G best may or may not be updated. Over here we say that if the P best of the ith particle, right. So, first we update the P best, and if we check it with the G best, right. So, if the P best has been updated, there may be a possibility that the G best also can be improved, right. So, in this case, if this satisfies that the P best of the ith particle, if it is better, right, we will update the G best and f of G best. Again, G best corresponds to the decision variable and f of G best corresponds to our fitness function value. So, let us say if I have 5 population members, right. So, there will be phi p best, and if it is a 4 dimensional problem, it will be a 5 cross 4 matrix. We can keep it as a 5 cross 4 matrix. F of p best will be 5 cross 1, because each solution will have one fitness function value. So, this is what, but G best at any given point of time, G best will be, G best indicates the decision variables, right. So, it will be 1 row and 4 columns corresponding to the 4 decision variables, whereas f of G best will be a 1 cross 1 scalar, right. So, you need to remember that G best and P best indicate the solutions, whereas f of G best and f of P best indicate the fitness function value. There is only one global best, the very name global suggests that there is only one global best. If there are 5 particles, there will be 5 P best corresponding to each particle, right. So, that is how we need to understand P best and G best. So, there is a small mistake in this slide, right. So, as we have discussed, global best would be only one, right. For the entire population there is only one global best. So, this is not of ith particle, right. Personal best is of, for every particle we have a personal best, but for the global best we have only one global best for the entire population, right. It is not global best of the ith particle. So, this is actually a typo over here. So, this equation which we use to update the velocity, right. If we see, it consists of 3 parts, part 1, part 2 and part 3. So, the first part is known as the momentum part, right. It serves as the memory of the previous flight, right. So, if I am going to find out v of t plus 1, right, this is going to be of tth iteration, the previous iteration. So, that way it serves as the memory of the previous flight, right. This component prevents the particle from drastically changing the direction, right, and it is biased towards the previous direction, because since it is dependent on vi of t, it is biased towards the previous direction, right. The second part is known as the cognitive part, right. It quantifies the performance of the ith particle relative to its own past performance, right. So, for each particle we have a p best, right. So, here we are taking the difference between the current position of the particle indicated by xi and its best location found in any generation. So, assume that we are in 25th generation, the first particle might have encountered its best location in the 3rd generation, right. So, this will be the value in the 3rd generation, and this will be its value in the previous generation, right. So, this will be the value whenever it has obtained its best location, right, whereas xi indicates its current position. By the use of the cognitive part, particles are drawn back to their own best position, because we are comparing it with its own best, right. So, this is more like nostalgia of the particle, right. They remember their best and they are always comparing with their own best. The third term is known as the social part, right. Social part, because this G best is coming from the global, right. So, it quantifies the performance of the ith particle relative to its to the neighbors. So, here we are considering the entire population to be neighbors, that is why we are updating G best with the help of all the P best. So, using this social part, the particles are drawn towards the best position determined by the group, and this resembles the group norm that each particle seeks to attain. Right. So, when we generate a new solution, 3 cases are possible. So, the first case is that we have generated a new solution which is not better than its personal best, right, and it is not better than the global best, right. So, for example, let us say for case 1, let us say the newly generated solution is 5 and 6 and the objective function is 61, right. Let us also assume that the P best before we got this new solution and its fitness function was 41, and the G best was 2, 3 with its f of G best as 13. So, now if we see, this new solution has an objective function of 61, and we are talking about now a minimization problem. So, this 61 is neither better than 41 nor better than 13, right. So, this solution will enter the population, right, but we will not update the P best or the G best, because this is not the best position obtained by this particle so far, because 4, 5 was a better position, right. So, we will retain this P best and FP best, and similarly since it is not better than this G best, we will retain the current G best and F best. So, in this case we are not supposed to update the F best or G best. Similarly, since we are not updating the solution, we are not supposed to update f of P best and f of G best. And so, this is one case wherein the solution is neither better than its personal best nor better than its global best. So, case 2, the solution is better than its own personal but poorer than its global best. So, in this case we will only update the p best, we will not update the g best, right, because it is not better than the global, it is only better than its best position so far. So, here if we see, let us say the new solution which we generated is 4, 3 and its fitness function let it be 25. So, and the p best, let us assume that the current p best and f of p best is 4, 5 and 41, right. So, now the solution which we have obtained 25 is actually better than this 41, right. So, we can update f p best and p best. Remember, we need to update the objective function value or the fitness function value as well as the decision variables, right. Whereas now if we compare this 25 with 13, right, 25 is not better than 13 because we are talking about a minimization problem. So, we do not need to update the g best, right. Similarly, if we are updating p best, we are also supposed to update f of p best, right. Since we are not updating g best, we do not update f of g best also, right. So, this is the second condition. The third case may be that the newly generated solution is actually better than its personal best as well as it is better than its global best. So, for example, take this case x is equal to 1, 3, right. So, it is like we had a solution, for that solution we generated a velocity and then we determined a new position. If the new position is 1, 3 and if the fitness function is 10, if we compare p best, previously we had 41, now we have 10 of this particular particle, right. So, p best, remember there are multiple p best, we need to compare with the p best of this first particle. If x is the first particle, we need to compare it with the first p best, right. So, since here if we see the solution 10 which we have obtained is better than the p best as well as than f of g best. So, in this case we will update both of them, the positions p best and g best, also we will update the respective objective function value f of p best and f of g best, right. So, both have to be updated. So, we will never come across this case wherein a solution is not better than its personal best, but it is better than its global best. So, this condition will not ever happen, right, because if something has to be better than global best, then obviously it is bettering, either it is the same as its personal best or it is better than the previous personal best. So, this case can never happen, the case 4 can never happen wherein the solution is not better than its personal best, but it is better than the global best, because global best is the best of the personal best. So, this case can never happen wherein a solution is not improving its personal best, but it is improving its global best, that would not happen. So, as we can see, particle swarm optimization is a fairly simple algorithm. I would say that it is even simpler than teaching learning based optimization, right. Despite that fact, we have taken particle swarm optimization after teaching learning based optimization is because of the tuning parameters. So, in teaching learning based optimization, we required only 2 user defined parameters. One was the population size and the second was termination criteria. In PSO, we need both of them. In addition to that, we need the acceleration coefficients which are 2 in number, C1 and C2, one associated with the cognitive part and another one associated with the social part, and also the inertia associated with its velocity, right. So, for anyone to execute particle swarm optimization, in addition to the details of the optimization problem, they also need to specify 5 parameters: inertia, 2 cognitive factors, the population size and the termination criteria, right. So, particle swarm optimization requires 5 parameters from the users. It is not always easy to specify these parameters for an arbitrary problem, though there are some basic guidelines, but it is not guaranteed that they will always work, right. So, one will have to solve the same problem with different settings, right, and as we know, for a stochastic algorithm we anyway need to run multiple times, right. Now, we not only have to run multiple times for a single setting, but we will also have to execute the problem for multiple settings, and for each setting we need to do multiple runs. So, that is a benefit of teaching learning based optimization, that we did not require multiple user defined parameters, we only required 2, here we require 5, right. Now that we have understood particle swarm optimization, let us now solve a small problem, right. So, that will help us to clarify the concepts further, right. So, for this we will take the same sphere function, with 4 decision variables. So, the objective function is x1 square plus x2 square plus x3 square plus x4 square, and the domain, let us take the domain also this to be the same what we considered in TLBO between 0 and 10. So, the first step is to fix the population size, inertia, acceleration coefficient, maximum iterations, right. So, let us say the population size is 5, the inertia to be 0.7, the acceleration coefficients to be 1.5 and 1.5 respectively, and that we would like to do 10 iterations, right. So, the next step is to generate random positions within the domain of the decision variable. So, we know the domain of the decision variable is 0 to 10. So, in this domain we need to generate 5 solutions, right. So, here we have taken integers so that it is easier to calculate, right. So, these are the 5 positions, right. So, for optimization we will be generally calling it as a population, but these are particles, because in particle swarm optimization these are considered to be 5 particles and these values are its position, right. So, these are the positions, which is nothing but the value of the decision variables, right, and this is the fitness function value for each of the solution, right. So, the next step is to initialize random velocities, right. So, we will also generate random velocities within the domain of the decision variable, right. So, domain of the decision variable we know 0 to 10, right. So, within 0 to 10 we need to generate velocity, right, velocity for each particle, right. So, for each particle means we have this 5 rows, right. This is the velocity of particle 1, this is the velocity of particle 2, particle 3, particle 4 and particle 5, right, and it is also a 5 cross 4 because this is NP cross D. D is the number of decision variable in our problems, right. So, remember velocity is not a scalar value, right. So, again we might feel that it is required to calculate the fitness function of this velocity, but no, fitness function of the velocity is not required. So, only the fitness function value of the positions are required, which we have already calculated over here, right. So, it is not necessary to calculate the fitness of this velocity, right. So, it is sufficient to calculate the fitness of the positions, right. So, next step is to determine the personal and global best of all the solutions. So, we have 5 particles, right. So, for each particle, since it is the first iteration, the personal best is considered to be the solution itself, right. So, for the first one 4008 is the personal best, because in the first iteration we do not have any historical information. So, the current solution itself is, the current direction itself is taken as the best direction, right. So, this is only for the first iteration, we will see that for the second iteration this will change, right. So, these are the P best for each particle. So, P best for the first particle is 4008, P best for the second particle is 3197, P best for the third particle is 0315, P best for the fourth particle is 2149 and P best for the fifth particle is 62839, and similarly we take the same objective function value, we do not need to recalculate them because we will get the same answers, right. So, we directly assign P as P best and F as F of P best only for the first iteration, right. After this first iteration is complete, you will see that the personal best values and the current positions can be different. So, once we are done with this, right, we need to identify the global best, right. So, the global best, if we see now in this vector of fitness, 35 is the global best, right. So, that is F of G best and the solution corresponding to it is 0315. So, this is the position, these are the velocities, these are the personal best, this is the G best, right. So, for position we have the fitness function, for P best we have F of P best, for G best we have F of G best. There is no need to calculate the fitness function of the velocities. The next step is to generate the velocities, right. So, we are now in the first iteration. So, the first solution in the first iteration. So, we need to find out its updated velocity, right. So, updated velocity Vi is going to be W, which we have fixed 0.7 into Vi. Vi we already have generated it randomly, so that is 9618. C1, it is a user defined constant, we have taken it as 1.5. R1 let us take it to be 0.4, 0.3, 0.9 and 0.5, right. And this vector, so the difference between the P best, so the current P best is 40808 and its F best is 80 and the current position is also 4008 and obviously that will also have the fitness of 80. So, this is the P best of 1 minus x of 1, right, plus C2 again that is a user defined parameter. In this case it has been set to 1.5. We need another set of random numbers. So, let that be 0.8, 0.2, 0.7 and 0.4. We require G best, which we have identified that it is 0315, and the current position, which is again 4008, right. So, if we plug those values into this, so 0.7 into 9618, in the first iteration P best and the solution are the same, the current direction and the current P best are the same, right. So, this will contribute to 0. This is going to happen, as you will see, this will happen for all the 5 solutions, but remember this will happen only in the first iteration. In the second iteration these two can be different, right, this P best of I and x of I can be different. So, this is going to contribute 0 as of now, right. The third part is C2 into the random numbers which we have selected, right, global best 0315 and the current solution 4008. So, if we evaluate this, we get this velocity, right. Once we have found the velocity, we will use this equation, the second equation, to update the position. So, the current position of the first particle is 4008, right, plus the newly determined velocity is 1.5, 5.1, 1.75 and 3.8, right. So, the new position is 5.5, 5.1, 1.75 and 11.8, right. So, this is the new position. From the perspective of optimization is, this is a new solution, right. So, since this is a new solution, we will have to see whether if the solution is within the bounds. So, in this case the bound that we are working with is for all the variables that it has to be below between 0 and 10, right. So, this particular variable is actually violating the bounds, right. So, we need to bring it back into the bound. So, again as we discussed previously, we will use the corner bounding strategy, right. Corner bounding strategy specifies that if something is violating the upper bound, so if particular variable is violating the upper bound, so the upper bound is here, if it is violating the upper bound, it is to be brought back to the upper bound, right. Same thing for the lower bound, that if it is violating the lower bound, it is to be pulled back to the lower bound. And if a solution happens to be between upper and lower bound, then we do not need to do anything, right. Right. So, in this case, this if we apply corner bounding, these 3 values will survive as such, only this 11.8 will be converted to 10, right. So, this is a solution, right. We can evaluate the objective function for this solution. So, that turns out to be 159.32. Remember, there is no greedy selection over here, whether the solution is better or not does not matter, it is to be included in the population or in the position. So, the position is to be definitely updated, right. So, the solution which we use to generate is this one, it has a fitness function of 80, right, whereas here the new solution which we have got is 159.32. Remember, we are working with a minimization problem. So, actually this 4008 is better than 5.5, 5.1, 1.75 and 10. Despite that fact, we will update the population, right. So, the population is to be updated, right. So, that is a fundamental difference between TLBO and particle swarm optimization, that for a solution to come into the population, we do not need to perform a greedy selection, right. So, this solution enters the population. Now, we need to see if we need to update the P best or the G best, right. So, since it is the first solution, we can only update P best 1 if it is a better solution, right. So, what we have got is 159.32 and what we had was 80, right. So, between these two, 80 is a better solution. So, that will be P best of 1, right. The solution in the population has changed, but the P best is not changed. So, for this particle, currently it has a position with a fitness of 159.32, but in the past it had a solution 4008 for which the fitness was 80, right. So, the personal best for the first particle is not to be updated. Why? Because the fitness that we had previously is better, right. So, we do not update this personal best one, right. So, now if we compare with global best also, you will realize that global best cannot be updated, because global best what we have is 35, right, and this solution has a fitness of 159.32. So, no update in G best, right. So, coming to the second solution, so the velocity is we had randomly generated, this is our x2, right. Our P best 2 is the same as x2 for the first generation at least, right, and this is our G best. So, if we apply this equation and calculate its velocity, right, we see that we get 0.35, 2.2, minus 7.5 and minus 0.6. Remember, we are not supposed to bound the velocity, right. The velocities can, though it is a 1 cross 4 vector which is similar to our position vector, we are not supposed to bound this, right. We will bound only the positions before calculating the objective function, right. So, in this case, if we find the position, it is 3.35, 3.2, 1.5, 6.4, which is well within the bounds. So, we do not need to bound it, right. And if we calculate the fitness of it, it happens that we get a fitness of 64.7. We are not supposed to compare. Remember, for the first solution we did not compare. So, similarly for the second solution also we are not going to compare with anything to update the population. The second solution is updated into the population, right. Now, we have, before going to the third solution, we need to see if we have to update the P best and G best. So, in this case, if we see the P best that we have is 3197 with a fitness of 140, right, but now I have a position which is better than this 140. So, we will update it, right, update P best, since the new solution is better than P best 2, right. So, for every solution we have its corresponding P best, right. So, but if we compare with G best is still 35 and the solution which we have obtained is 64.67. So, obviously 64.67 is not better than 35. So, we do not need to update the G best. So, coming to the third solution, similarly we need two sets of random numbers between 0 and 1, we generate it. The velocity V3 was generated randomly, we know the position, current position. For the first iteration it happens that the current position and the P best are same. We also have the G best over here, right. So, if we apply this equation, we get the velocity, we calculate the position and then we look at this position. If the position is violating the bounds, we update the position, not the velocity. So, we determine the objective function value to be 121.38, right. So, for the third solution, if we see, what we started was with 35, right, what we have ended up with is 121.38, but still it will enter the population, right, but there will not be any update of P best 3 or G best 3, because P best is 35, G best is also 35 and both of them are better than 121.38. So, I do not need to update P best 3 or G best. So, the previous value is retained. So, that is for the third solution. So, for the fourth solution, the velocity is again given, the position is known, the P best is known, the G best is known. If you apply this equation with these two sets of random numbers, you will get a velocity of this, right, and then we find a new solution or new position. Again we can find the objective function of this. So, if we find the objective function value of this, we get 28.13. So, the current solution which was used to generate this x4 is this one, 2149, right. It has a fitness of 102, it has 28.13. However, even if it had been 128.13, we will update it, right, as we have been stressing it time and again. The new solution will always be updated in the population, there is no greedy selection, right. So, this solution enters the population, right. So, that is done. Now, we need to compare the P best, right. So, the P best currently is 102 and the solution which we have is 28.3. So, it is better, right. So, we update the P best and F best, right. Similarly, in this case it happens that the newly generated solution, right, is also better than G best. So, the G best was 35 and what we have obtained is 28.13. So, 28.13 is less than 35. So, we also update the G best, right. So, if you see, we have tried to capture all the possible scenarios. One solution wherein no P best update, no G best update is required, another solution required P best update, another solution required G best update, right. So, the example has been carefully constructed so that we can we come across all the possible cases, right. So, similarly fifth case you can try it out, right. So, we know the velocity, the position, the current best, the P best of the fifth particle is known, the G best is known. Remember, this G best is not 35 which was the case when we started, right, but in the previous solution for the fourth solution the G best was updated. Since we have an updated G best, we will take into consideration the updated G best, right. So, with these two random numbers, if we calculate, the velocity will turn out to be this, right, and then we can find out the position. So here in this case 11.87 is out of bounds, so we will bound it to 10 using corner bounding because our upper bound is 10, right. Now we can find out the fitness function value of the fifth solution. In this case it works out to be 234.95, right. The solution which underwent this iteration was fifth solution which had 113, right. So what we have got is a poor solution. Despite that fact, the poor solution will enter because this is the newly generated solution. So this strategy is commonly known as mu comma lambda, that mu is a solution which we had and lambda is a solution which we generated. So among mu comma lambda, lambda will survive. It will survive even if it is bad, right. So this is not greedy selection. In greedy selection, only the solution which was better. So among mu and lambda, the one that was better survived, right. In mu comma lambda, here we have only one solution. We are comparing the first solution with first solution, the second solution with the secondly generated solution. So in this mu comma lambda, lambda always survives, right. It is not a greedy selection mechanism, right. So we have this 235.95. Now we need to compare with the p best. Now we need to decide whether p best and g best are to be updated. So p best currently is 113 and what we got is 235.95. So obviously 113 is better, so that is retained, right. This is not updated as p best. So this is not p best, right, though it is in the population. As the name itself indicates, it is the best position of the particle so far, right. Similarly, we will check for g best. G best that we currently have is 28.13 and the one that we obtained is 235.95. Since 28.13 is better, we will not update g best, right. So this completes one iteration of particle swarm optimization. So this was the population which we began with. This was the fitness function value. This was initially since there is no memory, the position of the particle themselves were considered to be the their personal best. The fitness function of the best position so far would be the same, right. This both would be the same in the first iteration, and we generated this velocity randomly within the bounds, right. And this was our g best because this was the best solution that we had, right. So we started with this. At the end of first iteration, this was our population. So every member would get updated. So here if you see, all the 5 rows are different from what we started, right. That is because newly generated solution is always taken into the population. We do not care if it is better or not, right. Updating of the population is with the new solution. So now if we see p best in some cases, right, we have been able to update it, right. The other 3 rows remain the same, right. The first row, the third row and the fifth row remain the same, because in this iteration, when we performed the first iteration, we got 2 solutions which were better than their past, right. So for example, here we had 140 and the new one which we have generated is 64.67. So obviously this is the personal best. For the second solution, the best solution which it has encountered so far is 64.67, right. Similarly, for the fourth solution, we had 102 and we were able to generate a solution of 28.13, right. So that has been updated over here. Whereas for the first solution, if we see, initially we started with a fitness function value of 80 and we generated another solution which was 159.32, right. So the one that we generated is actually bad. So the personal best for the first member remains the same, 4008 and 80, right. And this velocity, every time we determined a velocity, so that velocity is to be used for the second generation or second iteration. So this is the velocity that we had generated for each and every solution, and this is our g best, right. G best is what is the best in the p best. So p best, we have 5 solutions, the personal best of each is known. So the global best is the minimum among that, since we are solving a minimization problem. So that completes one iteration, right. So second iteration, the same values whatever you have seen previously have been given over here. So the second iteration if we perform, so here you will be able to see in the first iteration this term was cancelling out, right. P best minus xi was cancelling out, right. But in the second iteration, now we have the personal best to be different, right. The personal best is 4008 and the solution is 5.5, 5.1, 1.7, 10, right. So this term does not always go to 0, only in the first iteration it goes to 0, right. So we find the velocity we find the new position. Since this particular variable has a value which is out of its bound, we will bound it, we will calculate its objective function, it is 130.53. What we started was 159.32, what we have got is 130.53. Irrespective of whether it is better or not, it will find a place in the population, right. So, it finds a place in the population, right. For the first member, the history so far says that 80 was its personal best. What we have now currently got is 130.53, which is still bad than 80, right. So, we do not need to update. So, we do not update. Similarly, there is no update in GBEST because the GBEST which we have is 28.13 and the solution which we have generated has a fitness of 130.53, right. So, similarly you can proceed for the other solutions. So, as you can see, it is a extremely simple algorithm, right. Only thing that we need to keep in mind is that the newly generated solution is always going to be accepted into the population. It does not matter whether it is better or bad. So, the new solution will always be used into the population, and for each member we keep a track of its personal best, right, and the global best is the solution which is the best among all the personal best. So, that concludes this example. You can go and try out the couple of more iterations and see if you are able to implement it, right. Now, as we have understood the working of particle sum optimization, let us have a look at its pseudocode, right. So, for us to execute particle sum optimization, obviously we need an objective function value or the fitness function value. We need to know the number of decision variables and their corresponding lower and upper bounds, right. We need to fix the particle size. So, these three things come as part of the problem. As and when someone says that they have an optimization problem to solve, they need to know the decision variables, the lower and upper bound and the fitness function. So, that is part of the problem, whereas this rest 5 parameters are to be given by the user. And so, we need to specify the population size, the termination criteria, in this case the number of iterations, the inertia W and the acceleration coefficient C1 and C2. Right. So, the first step is to initialize a random population within the bounds and also initialize the velocity, right. So, both of these are NP cross D, right. Since our population size is NP, the number of decision variable let it be D. So, D will be the length of either LB or UB, right. So, NP cross D. So, population as well as will be a matrix of NP cross D, right. And since we are generating, we will straight away generate within their bounds, right. Once we have the population, we need to evaluate its objective function value. Once we have evaluated the objective function value of P, we can assign P best and F best. So, P best will be nothing but the random population and the fitness of the corresponding P best would be nothing but the fitness of the objective function value. So, we do not need to go and determine the fitness of P best again, right, because it will be the same as the fitness function of the population, right. And remember, we are not required to determine the fitness of the velocity, right. Though it is NP cross D, we do not require its fitness, right. So, the next step is to identify the solution with best fitness and assign that solution as G best and FG best. So, looking at this f of P best, we will find what is the least value. So, that least value will be nothing but f of G best, and the solution corresponding to that least value will be our G best. So, this is the global best solution and this is the fitness corresponding to that global best solution. So, the next step is to perform the iterations, right. So, for I equal to 1 to T and end. So, whatever is there within this loop will be performed T times, right. So, if for each iteration we need to perform the operation for each member. So, we have another for loop for I is equal to 1 to NP, where NP is the number of particles. So, the next step is to determine the velocity Vi of the particle using this equation. So, initial W is a constant, C1, C2 have been user defined. So, we need to generate R1, R2, those are random numbers between 0 and 1 and their dimension will be 1 cross D. So, we will require D random numbers here and D random numbers here, 1 for each variable. We know P best I, we know G best. So, we will be able to apply this equation to determine the velocity. Once the velocity is determined, we need to find the new position using this equation, right. So, first find the velocity and then find the position, right. So, after finding the position we need to bound it if required, right. So, if it is violating the upper or lower bound, we need to bound it and then determine the objective function value of the particle, right. So, once this is determined, it will be updated in the population. So, the newly generated position will be updated inside the population. So, remember, as we have said multiple times, there is no greedy selection over here. The position of that particle is updated. We need to update the population by including xi and also replace fi in the vector f. The next step is to check whether the newly generated solution, if it is better than the p best, right. So, we will be employing this condition that if the newly generated solution, if it has a fitness of fi, if it is lower than f of p best I, then we will update it. We will update the p best and f best, right, else we will not update the p best and f best. So, this I corresponds to the particle, it is not corresponding to the iteration is t. Similarly, we will check for the g best, right. If we have been able to update the p best, then we actually see if the p best of the current member is actually less than the global best which we have determined so far. If that is the case, then we will update it, else we will retain the current g best and f of g best, right. So, this is the pseudo code of particle swarm optimization. As we can see, it would be fairly simple to implement this code. Right. So, here these three steps correspond to the generating a solution, right, and this is the memorizing, right. We are checking if it is better than the current p best and the current g best. If it is better, then we will update, else we will not update. So, that is the memorizing portion. Now, let us look at the fitness function evaluation, right. So, in how many places are we evaluating the fitness function, right. So, over here initially we evaluate the fitness function for NP times, right. We generate NP random population members. So, we need to evaluate their fitness. So, we will be using the fitness function evaluation NP times, and we will be using one time for every member, right, and we have NP members and we will do it for t times. So, for this iteration loop, we will be performing it for NP into t times, and we have initial NP evaluation. So, if you see, it is different from teaching learning based optimization. So, now let us see what is the significance of this parameter W, C1, C2, right. So, there are various cases. So, if C1 and C2 are 0, right. So, the typical outcome that we expect is that the particles will move in the same direction. So, here if we see, if we eliminate the second and the third term, if that is eliminated because C1 and C2 is equal to 0, then if we see W into V will be in the same direction, it will not change the direction, right. So, if it keeps moving in the same direction, then either it will hit the lower bound or the upper bound, and then we will do a corner bounding strategy to bring it back to the bounds, right. That is what will happen if C1 and C2 are 0. If C1 is greater than 0 and C2 is equal to 0. So, in this case we are not relying on the global best, we are only relying on the particle best. So, what would happen is the particles will become independent hill climbers. So, the global knowledge they do not have, they only have their own personal best, and they will get stuck around their own personal best. So, that is they are looking around their own personal best. So, that is more like performing a local search in that particular region, right. Again, the next case is wherein C1 is equal to 0 and C2 is greater than 0. In that case, we are not relying on the personal best, we are relying only on the global best. So, in this case what happens is that entire swarm becomes one stochastic hill climber, and all the particles will get attracted to a single point. Now, this single point may or may not be the global optima, right. It is like we are just trusting the solution which is the best so far, right. So, all the particles will try to reach that particular solution because we are not considering p best into account, right. So, that is what will happen if C1 is equal to 0 and C2 is greater than 0. So, if C1 is equal to C2, then the particle is said to be attracted towards the average of p best and g best, right. Similarly, if C1 is much greater than C2, right, then the particles are attracted towards its p best, and this will result in excessive wandering, right. So, this is similar to the second case, though it is not 0, but it is insignificant when compared to C1, and in the case C1 being significantly lower than C2, the particle will get attracted towards G best, and this usually causes premature convergence towards optima, right. For low values of C1 and C2, there will be minor perturbations. So, the particle trajectories are smooth. For high values of C1 and C2, we will have abrupt movements. So, this slide is primarily based on from this book, Computational Intelligence and Introduction, from John Wiley and Sons. For further details on this, you can look into this book. So, now let us actually see the impact of the various parameters. So, this is a function known as Tilbach-Tang function. It is actually a scalable function, right, but we will be showing it for two variables, right. So, all the variables have the domain of minus phi to phi, right. In this case, in our case, for this discussion we will be taking d as 2. So, we have two decision variable, and this is the objective function, right, half summation of I equal to 1 to d x1 power 4 minus 16 x1 square plus 5 x1 plus again x2 to the power 4 minus 16 x2 square plus 5 x2, right. So, the global minima of this function irrespective of the number of decision variable is located at this point minus 2.903 comma minus 2.903 for a two variable problem, and the objective function value is minus 39.6166, right. So, if we see, these are the contour plots, right. So, we are considering three cases. In one case wherein C1 is equal to 0, right, this case is C2 equal to 0, and in this case we have C1 and C2 equal to 1.5, and the inertia in all three cases is 0.7, right. So, these are the three cases we are studying. So, this is the initial population before we begin the iteration. So, with a population size of 10 and for the termination criteria of 50 iterations, we will see what will happen, right. So, the optima, if we see, it is located somewhere over here minus 2.9 comma minus 2.9. So, it will be somewhere over here, the optima, right. So, we will see in on all three conditions what happens. So, let us first look at the first figure, right. So, the particles are moving, right. So, the optima is over here, right. So, however, the solutions are converging over here. So, when C1 is equal to 0, what we are saying is the global best is not considered, right. So, here we have given the equation. So, it relies only on the G best, right. So, it happens that one particular particle had this as its personal best, and that become its G best, and all particles converged over here in this particular region, despite the fact that the optima is over here, right. So, that is what happens when we rely only on the global best and not on the personal best. So, let us see in the second case what happens in the second case, right. So, in the second case, if we see over here in this plot, right. So, we see all the particles are individually moving in their own region, they do not have the global knowledge. So, if C2 is equal to 0, that means we are ignoring in this term. So, all the particles are relying on their own personal best. So, in that case, if we see at the end of 50 iterations, none of the particles are over here, right, and all of the particles were individually moving. So, we can see that once again. So, right. So, the particles are never converging, they are just following their own p best. So, right now the particles are not even moving probably. So, the third case is wherein C1 is equal to 1.5, C2 is equal to 1.5, which means that both of these terms are active. The p best term is also active, the g best term is also active. If we run this again, so if we see the third case, all the particles are converging towards the global optima, which is located at minus 2.9 comma minus 2.9, right. So, all the particles are indeed reaching that particular global optima or almost close to the global optima. The values might be slightly different. So, this shows that the personal best and the G best contribute to reach the optimal solution, right. So, next we will be looking into this factor inertia weight. It is used to control the impact of previous velocity in new directions, right. So, the velocity in this iteration is a function of velocity of previous iteration, and this W will help us to control the impact of previous velocity in the new direction, because this velocity is again going to be added to our position, right. So, that is why we say that it helps us to control the impact of previous velocity in new direction. right. So, it is used to balance exploration and exploitation. So, a large inertia weight will result in exploration, right, the swarm will diverge, and small values of inertia will cause exploitation, that is it will decelerate the particles. There will not be huge changes, but there will be just minor changes. So, the value of W can be a constant. So, very often it is taken to be a constant. It can also be varied iteration to iteration. So, in this case alpha is a damping factor which is to be given by the user. So, now in addition to the population size, the number of iterations, W which is the inertia weight, and the acceleration coefficient, we also need to provide the damping ratio, right. So, what this will do is that it will decrease W as the iteration progresses, it will decrease the W depending upon this damping ratio. So, that is one scheme. Another scheme is wherein W is linearly decreased between a W max and W min, right. So, if we are going to use that is this scheme, then in addition to the 5 parameters that we need to give, we will also have to give W min and W max, right. With this relation, if you see, as the number of iterations progress, W will decrease, right, from W max to W min, right. It will be truncated at W min, it will not go below W min, right. So, it will be truncated at W min. So, as iteration progress, the inertia weight is linearly decreased. So, very often people use this scheme too, right. And then we have another scheme called as the use of constriction coefficients. So, now in addition to this 5 tuning parameters, we will also have to decide on how we are going to use W. Are we going to use a constant value, or are we going to employ a damping ratio in every iteration, or are we going to linearly decrease it? If we are going to linearly decrease it, we need to decide on W max, W min, and if we use constriction coefficient, you will see that there will be few more parameters that we will have to specify, right. So, as you can see, we will have to provide a large number of user defined parameters in addition to the 2 which was common to teaching learning based optimization, and it is difficult to specify which one of this scheme will work for an arbitrary problem, right. And for many people who use optimization as a black box tool, it even more becomes difficult for them to tune this parameters, that what value of W will best work for them. Since they may not even know what is happening inside the algorithm, it becomes very difficult for them to tune this, right. So, very often this is why some algorithms which might be very good when the authors propose, it is not widely accepted by the user community, especially those who are applying optimization in a black box sense. So, let us look into the constriction coefficients. So, these constriction coefficients are implemented to prevent explosion, and it also aids in converging to an optima. So, constriction coefficient rule specifies that we can set W to be chi, C1 as chi into phi 1 and C2 as chi into phi 2, right. So, the usual values of k phi 1 and phi 2 are taken as 1, 2.05 and 2.05. So, these values which we take should satisfy these two relations, that k should be between 0 and 1 and phi should be greater than 4, and phi is nothing but summation of phi 1 and phi 2, right, and chi can be calculated using this formula. So, once we calculate chi, we can find out the value of W C1 and C2, right. So, in this case we can say that we have a scheme to determine the value of W C1 C2. So, but we need to specify these 3 values then, right, and these 3 values which we specify should satisfy this relation. So, we may not have to directly specify these values, but we will have to specify k phi 1 and phi 2, right. So, still the number of tuning parameters is still the same. So, you can further read on this constriction coefficients in this article which appeared in IEEE Transactions on Evolutionary Computation. Also, you can look at this YouTube video in which they demonstrate the working of constriction coefficients. So, now let us study the impact of the inertia weight, right. So, here we have 3 cases for the same problem which we have discussed, right. So, C1 and C2 are constant for all the 3 cases, it is set at 1.5. The inertia weight is also set to 3 constant values, W is equal to 0, W is equal to 0.8 and W is equal to 1. right now we are not varying W with respect to the iteration, it's a constant value, right. So now if we see in this 3 contour plots, so remember the optima is somewhere over here, minus 2.9 comma minus 2.9. So in the first case with W is equal to 0, we see that since the particle do not have this W into Vi component, they tend to get stuck at a local optima as shown in this first one, right. In the second one we can see in this figure we can see when W is equal to 0.8, the solutions are scattered over here, right. It is close to the global, close to the globally optimal solution, and in the third case also if we see it is also closer over here. So this basically shows us that W does have an impact on the performance of the algorithm, right. So with 0.8 we see that it is converged, it is more closer to the global optima when compared to ones. So W has to be appropriately specified because it has an impact on the performance of the algorithm. Right. So in this case we show two strategies to vary W, right. Again C1 and C2, still we are dealing with the same problem. C1 and C2 are fixed at 1.5, 1.5. In this case we will be using a damping ratio. In the first case we will be using a damping ratio. In the second case we will be varying the inertia weight linearly from 0.9 to 0.4, right. And here we have used a damping ratio of 0.99. For this function and these settings, if we execute particle swarm optimization, we can see here that W is decreasing, right. So over here we can see that for linearly varying W, we have converged to an optima fairly quickly when compared to this damping ratio, right. So we can just once again have a look at it. So we can see at what iteration is it becoming closer. So for 23rd iteration, things were not even appearing over here when we are using damping ratio, right. So by pretty early we are able to get the optimal solution in when we vary the inertia weight linearly. This shows the use of constriction coefficients. So here these values of C1 and C2 have been derived using the suggested value in literature. Phi 1 is equal to phi 2 is equal to 2.05 and k is equal to 1. We know the constriction equations, right. If we plug this into the chi equation, we will be able to get the value of chi, and using chi we can set all these 3 parameters W, C1 and C2, right. So over here if we see it performs fairly better, it will be able to reach the globally optimal solution, which is somewhere here, right, minus 2.92 to minus 2.92. So 50 iterations, at least some of the solutions have been able to come closer to the global optima. So that concludes the study of the impact of inertia weight C1 and C2, right. So these do have an impact on the performance of the algorithm, but it is not straightforward to set these values. We have only showed you whatever is usually considered in literature. There are further studies on how to tune these values, right. So that is why we started with TLBO, because the number of tuning parameters is less. So that is one of the advantage of TLBO, that a user need not spend time in tuning the parameters. There are only 2, and termination criteria is fairly straightforward, like someone could terminate based on the number of iterations, or someone can terminate based on the amount of time that they have to solve that particular optimization problem, right. So only 2 parameters are needed in TLBO, whereas here we have 5 parameters, and for tuning C1, C2 and W there are schemes available, but then there are multiple schemes. Which scheme has to be used for the problem at hand is not clear, right. So though PSO is simpler than TLBO in its implementation, the tuning of these factors can become very difficult for many problems. So before concluding particle swarm optimization, let us quickly make a comparison between teaching learning based optimization and particle swarm optimization. So in teaching learning based optimization we had 2 phases, teacher phase and learner phase, whereas in particle swarm optimization as such we did not have any phase, it is just that we had to update the position and the velocity. In TLBO as well as in PSO, the convergence is monotonic, right. In TLBO it is monotonic because we employ a greedy selection strategy that any member which enters the population should be better than the member which is leaving the population, right. So, that way monotonic convergence is ensured in teaching learning based optimization. In particle swarm optimization we do not have a greedy selection to update the population, but we do greedy mechanism for updating G best and P best. Only if a solution is better than G best will we update G best. So, G best will at any iteration G best will correspond to the best solution obtained so far. So, if you are going to plot iteration versus G best value, it will be monotonically converging, right. So, the parameters in TLBO was only two parameters, population size and termination criteria, right. Over here we need to specify population size, termination criteria, inertia weight, and acceleration coefficient. So, there are two acceleration coefficients, remember, C1 and C2. As we have looked into inertia weight, it can be kept a constant, or it can be linearly varied, or we can use a damping mechanism, right. So, again the choice of that becomes a user defined value, right, as to which scheme has to be used to update inertia weight, whether we want to update the inertia weight or not, and if we want to update the inertia weight in every iteration, then what scheme has to be employed. So, that becomes another user specified value, right. So, in TLBO when we were generating new solutions, we were using mean and the best solution in teacher phase, right, and in partner phase we were using another solution. So, the other solution and best solution were part of the population itself, whereas in particle swarm optimization we generate a solution using the velocity vector. Again when we will calculating the velocity, we use the personal best as well as the global best. These personal best and global best need not be part of the population, right, because we are not employing a greedy scheme to update the population. The personal best and global best may not even be a part of population. In TLBO we generated a new solution in the teacher phase as well as in the learner phase. So, in one iteration for one population member we explore two new solutions, whereas in particle swarm optimization for one iteration for every member we explore only one new solution, right. So, that is why we say the change in these values, right, NP plus 2 NPT, that is the number of total functional evaluations in TLBO, whereas in particle swarm optimization the number of functional evaluation is given by NP plus NPT, right. So, since here we do it twice, this 2 appears in TLBO, whereas here it does not appear. So, the selection mechanism used in TLBO was a greedy selection mechanism, right. The population was updated using a greedy mechanism, whereas in particle swarm optimization the new solution was always accepted. It is more like a mu comma lambda, again mu being a single solution and lambda being a single solution, right. So, in both of them the newly generated solution was always accepted. So, number of functional evaluation as we just discussed, that we evaluate the solution once in teacher phase and once in learner phase for every member, that gives us 2 NP for every iteration. So, for T iteration we get 2 NPT, and then we have initially NP evaluations, okay. This is the expression that we have previously determined. Over here for every iteration for every population member we only explore one new solution, right. So, this NPT is for that and this NP is initial population member. So, now we know two algorithms, right. So, now you can also appreciate the fact that why algorithms should not be compared with same number of iterations. So, performing 50 iterations of TLBO requires different number of functional evaluations than 50 iterations of particle swarm optimization, right. So, if we take a population size of let us say 50, right, and let us say we are doing 10 iterations, right. So, this is 2 into 50 into 10 in this case, right. So, this will be 500, 1000, 1050 evaluations, right. Over here if we see 50 plus 50 into 10, so it will be 550, right. So, if we want this to be equal, right, if we want the total number of functional evaluations to be equal, then we will have to perform twice the number of generations. So, this is some of the further reading on PSO, right. You can read the actual paper particle swarm optimization published in 1995. You can also look into this paper in IEEE Transactions on Evolutionary Computation, wherein they study in detail about the explosion stability and convergence. So, that would give you better idea on how to select the values of W, C1 and C2. Remember, this is an introductory course on optimization, particularly on meta heuristic techniques. So, we are not going into details about how to tune it, but you should know that it has to be tuned appropriately, right. So, how to handle multiple objectives in particle swarm optimization, again it appeared in IEEE Transaction on Evolutionary Computation. You can look into it for solving multi-objective optimization, and this is a more recent paper called as DNLPSO, Dynamic Neighborhood Learning Based Particle Swarm Optimization. So, this is a recent variant. You can, if you are interested, you can look into that and see what are the modifications that have been done by the authors. So, with that we conclude this session on particle swarm optimization. I hope you would have found it interesting. In the next session, we will use MATLAB to implement particle swarm optimization. Again, it is going to be fairly simple one. Once you know the pseudocode well, we will be able to quickly implement it. So, thank you.